This video describes the firmware development flow for Microsemi SoC FPGAs using Libero SoC version 11.7 Service Pack 1 or later and SoftConsole 4.0. This video demonstrates how to export the firmware configuration files and firmware drivers and generate sample projects from Libero SoC, then open the sample project in SoftConsole 4.0, build the application, and debug on a target board. This figure shows the Microsemi embedded design flow. The FPGA design is implemented in Libero SoC. Microsemi's Libero SoC is a comprehensive software toolset for designing with Microsemi FPGA and SoC FPGAs. Libero SoC supports Microsemi's Igloo2, SmartFusion2, SmartFusion, Igloo, ProASIC 3, and Fusion families, managing the entire design flow from design entry, synthesis and simulation, through place and route, timing and power analysis with integration of the embedded design flow. After the design is verified for functionality, performance, and optionally for power consumption, the target silicon is programmed. Firmware cores are pre-packaged bundles of embedded firmware header and source files and documentation supporting specific embedded firmware development tools, CPU targets, direct cores, and SmartFusion or SmartFusion2 microcontroller subsystem peripherals and services. Firmware cores fall into two main categories: hardware abstraction layers and drivers. Hardware abstraction layers include hardware abstraction layer underlying the direct core peripheral drivers, the SmartFusion SimSys PAL, and the SmartFusion2 SimSys hardware abstraction layer. The hardware abstraction layer firmware cores provide a base platform on which other peripheral drivers sit, C startup code that runs before main is called, which carries out initialization of the hardware and runtime firmware platforms, and useful linker scripts. Linker scripts are files that contain commands that direct the linker tool to generate executable files that have data and code sections in the desired memory addresses. The SimSys HAL firmware cores include a number of useful example linker scripts for creating programs that can be programmed into various memory targets. These linker scripts can be reused as is or adapted to the needs of a specific target. Drivers include firmware drivers for FPGA fabric-based direct core peripherals, firmware drivers for SmartFusion MSS peripherals, and firmware drivers for SmartFusion2 MSS peripherals and system services. Firmware cores are published through the Microsemi firmware repository. Libero SoC provides support for locating, browsing, downloading, and generating firmware core drivers, sample projects, and documentation. Firmware cores facilitate and accelerate embedded firmware development by eliminating the need to write low-level code that interacts with the raw hardware platform. Sample projects can also be exported from Libero SoC. Sample projects demonstrate how a firmware core can be integrated in a project. They are a useful starting point for becoming familiar with the software development tool and as a reference point and basis for the creation of custom application projects. The firmware cores and configuration files that are bundled with the sample projects are not dynamically created by Libero. Firmware cores and configuration files that are exported from Libero SoC match the silicon design. The firmware cores and firmware configuration files that match the hardware design must be imported into the sample project to ensure the firmware project matches the hardware. These files must be re-exported if the design is modified and re-imported into the firmware project to ensure the firmware project stays in sync with the hardware. After building the application, the code is downloaded to the target board and the application can be debugged on the target silicon. This video shows SoftConsole 4.0, which is Microsemi's free software development environment that enables the rapid production of C and C++ executables for Microsemi FPGAs using ARM Cortex-M3 and Cortex-M1 processors. The steps to use a sample project in SoftConsole 4.0 are 1. Export one or more firmware sample projects from Libero SoC. 2. Export the firmware cores and firmware configuration files from Libero SoC. 3. Open SoftConsole 4.0 and import the sample project into the workspace. Import the firmware cores and firmware configuration files that were exported from Libero into the sample project. 4. Verify the SoftConsole project build settings, making changes if needed. 5. Build the project. And 6. Create a debug launch configuration and launch the SoftConsole OCD debugger. This is a block diagram of the tutorial design. This design includes the SmartFusion2 microcontroller subsystem and a PWM fabric peripheral, core PWM. The clock is provided by one of the SmartFusion2 fabric PLLs. The reference clock for the PLL is the SmartFusion2 50 MHz RC oscillator. The fabric PWM will be used to drive an LED on the target board. This design was implemented using the Microsemi System Builder tool. This is the Libero SoC project for the demo design. Here you can see the Smart Design canvas with the design visible. The green check marks in the design flow window indicate that all the implementation steps have been completed, including programming. Sample firmware projects for IAR Embedded Workbench for ARM, Kyle MDK ARM, SoftConsole 3.4, and SoftConsole 4.0 can be exported from Libero SoC. Expand handoff design for firmware development in the Libero SoC Design Flow tab and select Configure Firmware Cores. Right-click and select Run. The Design Firmware tab will open, displaying firmware cores for the peripherals used in the design. Any cores that are missing from the vault are displayed in italics. Download any missing cores by right-clicking on the row showing the missing core and selecting Download All Cores, or by clicking the Download button. Right-clicking on one of the rows opens a menu with options to disable generation of the driver, open documentation for the drivers, including release notes and the user guide, or generate a driver sample project. For my design, I'll create a core PWM sample project for SoftConsole 4.0 by right-clicking on the core PWM driver row and selecting Generate Sample Project, Cortex M3, SoftConsole 4.0, PWM Slow Blink. A dialog box will open showing a list of all the files that were generated and their location. Sample projects can also be created from the Microsemi firmware catalog, which installs with Libero SoC. The next step is to export the firmware cores and firmware configuration files for the silicon design from Libero SoC. Select Export Firmware under Handoff Design for Firmware Development on the Libero SoC Design Flow tab, then right-click and select Export Firmware. The Export Firmware dialog box will open. The default file location is a folder named Firmware within the Libero SoC project. The firmware cores and configuration files are tool chain dependent. Select the tool chain from the pull-down menu. I'll select SoftConsole 4.0 for my project. Confirm that the radio button next to Export Hardware Configuration and Firmware Drivers is selected, then click OK to export the files. A dialog box will indicate that the firmware configuration files were exported successfully. The Libero SoC report view will open and show the memory map for the design. This will be useful later when developing the application code. The firmware configuration files and firmware cores are visible on the Libero SoC Files tab in the Firmware folder. The sample project will be visible on the Files tab in the SoftConsole folder. Now that I've exported the firmware cores and firmware configuration files and generated the PWM sample project from Libero SoC, the next step is to open SoftConsole 4.0, specify the workspace, and import the PWM sample project. Open SoftConsole 4.0 from the Start menu or by clicking the SoftConsole shortcut. The Workspace launcher may open. The workspace is the main working folder which stores information about projects in the workspace, user preferences, cache data for Eclipse plugins, etc. Multiple workspaces can be created, but only a single workspace can be opened at any one time. When using SoftConsole, all operations take place in the context of the open workspace. A workspace can contain 0 or more projects. Projects are used for builds, version management, sharing, and resource organization. Projects map to directories in the file system. When you create a project, you specify a location for it in the file system. If the SoftConsole Workspace Launcher opens, navigate to the location for the workspace. You can select Use this as the default and do not ask again to prevent the Workspace Launcher from opening each time SoftConsole is launched. For this demo, the sample project was saved in a folder named SoftConsole under the Libero project. I'll navigate to this folder, then click OK to set the workspace location. The File, Switch Workspace menu option can be used to switch to a different workspace or create a new workspace. Import the PWM sample project by selecting File, Import from the SoftConsole menu. The Import dialog box will open. Expand General and select Existing Projects into Workspace, then click Next. Click the Browse button and navigate to the location of the PWM sample project. The project name will appear in the Project section of the Import dialog box. Confirm the box to the left of the project name is checked, and check Copy Projects into Workspace in the Options field, then click Finish. Click the triangle next to the project name in the Project Explorer to expand the project. The SimSys, Drivers, Drivers Config, and HAL folders will be visible. After importing the PWM sample project into the SoftConsole workspace, the next step is to import the firmware cores and firmware configuration files that were exported from Libero SoC. This step is required to ensure the firmware project matches the hardware configuration and must be repeated if the hardware configuration is changed. The files can be imported from the SoftConsole file menu, but here's another method which is a bit faster. Open Windows Explorer and navigate to the location of the firmware files that were exported. For this demo design, they're in the firmware folder of the Libero SoC project. Hold the Control key and select the SimSys, Drivers, Drivers Config, and HAL folders in Windows Explorer. While holding the left mouse button, drag the folders into the SoftConsole Project Explorer view and click the project name. Select Copy Files and Folders in the File and Folder Operation dialog box and click OK. Select Yes to All when prompted about overwriting the existing files. At this point, I have imported the PWM sample project, the SimSys and hardware abstraction layer, firmware drivers and driver configuration files into the SoftConsole project. The SimSys is an abstraction layer for the core Cortex-M features and MSS peripherals. The HAL is an abstraction layer for the direct core fabric peripherals. The PWM sample project includes a platform header file that contains the base address of the fabric PWM peripheral. This file is bundled with the sample project rather than being created dynamically by Libero, so it may need to be modified to ensure it matches the hardware design. Double-click platform.h in the Project Explorer view to open the file in the SoftConsole editor. Scroll in the file and locate core PWM_base_ADDR. Compare the address of core PWM_base_ADDR in the platform.h file with the address of core PWM_0_0 shown in the memory map of the design datasheet in the Libero SoC report view. If the Libero reports view is not visible, open it by selecting Design Reports. After modifying the base address for core PWM, save the platform.h file by clicking the Save icon on the toolbar or selecting File, Save from the SoftConsole menu. Before building the project, a few project build settings must be entered in SoftConsole. The project build settings specify details of the number and type of build configurations supported by the project and the tools and configuration options used to build these. The build settings will vary from project to project. The build settings are preset in the firmware sample projects, and they provide examples of how the project build settings can be configured and are a useful place to start when creating firmware for a CPU-based system. Some settings are specific to a particular build configuration, while others apply to all build configurations. By default, SoftConsole projects normally contain two build configurations named Debug and Release. The Debug build configuration facilitates interactive and iterative download to and debugging on the target hardware. Most or all optimization is disabled, and most or all debugging symbolic information is enabled. This configuration is usually linked with linker settings or a linker script that facilitates download to and debugging from embedded or external RAM. The release build configuration facilitates the creation of production program images for storage in and execution from a suitable internal or external flash memory. Most or all of the optimization is enabled, and debugging is often disabled. This configuration may be linked with a linker script that facilitates interactive download to and debugging on the target platform, but the presence of optimization and or the lack of debug symbolic information may make accurate debugging, such as line tracking, difficult. These build configurations are simply conventional. It is perfectly feasible to have as many varied build configurations as required by a specific program and target system. Select the project name in the Project Explorer and then select Properties from the Project menu to open the Properties for PWM Blink dialog box. Expand the C build category and then select Settings. First, we'll examine the build settings that apply to all build configurations. Select All Configurations from the Configurations pull-down menu, then select Miscellaneous under Cross-Arm-C Compiler. Confirm the Other Compiler Flags field contains --specs equal simsys.specs. This setting is required for SmartFusion2 projects to allow the preprocessor to find the toolchain SimSys header files. Any preprocessor defines, symbols, or includes that are needed can be entered under Tool Settings, Cross-ARM-C Compiler. For this sample project, the paths are already entered. If any paths are missing, they can be added. Click the Add symbol next to Include Paths. Click the Workspace button in the Add Directory Path dialog box. The Folder Selection dialog box will open. Expand the PWM Blink folder and select the desired folder, then click OK. Click OK in the Add Directory Path dialog box. Repeat the previous step to add additional directory paths as needed. The paths will be visible on the Tool Settings tab of the Properties dialog box under Cross-ARM-C Compiler Includes in the Include Paths section. NewLib is the standard library bundled with SoftConsole, and it is optimized for use in resource memory-constrained bare metal embedded firmware environments. NewLib also comes with a nano version, which is even smaller at the cost of omitting some functionality which may be rarely used, such as the full range of printf formatting options. In many cases, it makes sense to use a NewLib Nano and only to switch to the full NewLib if necessary, because using NewLib Nano can significantly reduce the compiled and linked programs which use standard library features. To use NewLib Nano, check the Tool Settings, Cross-ARM-C Linker, Miscellaneous, Use NewLib Nano option. The debug and release build configurations in the sample projects use different linker scripts. Select Debug from the Configurations pull-down menu, then select General under Cross-ARM-C Linker. The script file section should contain the text shown here. This linker script builds an executable that executes from the SmartFusion2 embedded SRAM. For projects created from scratch, add the path to the linker script by clicking the Add symbol next to Script Files. Click the Workspace button in the Add File Path dialog box. The File Selection dialog box will open. Navigate to the PWM Blink, SimSys, Startup_GCC folder and select a suitable linker script, then click OK. Select Release from the Configurations pull-down menu, and then select General under Cross-ARM-C Linker. Confirm that the script file section contains the text shown here. This linker script builds an executable that executes from the SmartFusion2 embedded non-volatile memory. For projects created from scratch, add the path to the desired linker script as described earlier. Additional build configurations can be created by clicking the Manage Configurations button, then selecting New in the Manage Configurations dialog box. After confirming the project settings, click OK to close the Properties for PWM Blink dialog box. Build the project by selecting Build All from the Project menu or by clicking the Build All icon on the toolbar. The Problems view displays build warnings and errors and supports quick navigation to the source of problems. The Console view displays project build and debug launch logging, status, and error messages. The Problems and Console views can be maximized to make it easier to read the messages. Create a debug launch configuration prior to launching the OCD debugger to debug on the target board. Most of the default settings for a debug launch configuration can be left as they are, but a few need to be manually configured. Select the project name in the Project Explorer, and then select Debug Configurations from the SoftConsole Run menu. In the Debug Configurations dialog box, double-click GDB Open OCD Debugging, or click the New Launch Configuration button to create a new debug launch configuration for the project. Select the Main tab in the Debug Configurations dialog box. Ensure that the C++ application field contains the correct project name and executable name. Note that changing the directory separator from backslash to / aids in portability, as the backslash works for Windows but generates an error in Linux. Using a / works for both Windows and Linux. Next, select the Debugger tab. Here it is critical that the Config Options field contains the correct command line options and script to be passed to OpenOCD. The default settings here work for SmartFusion or SmartFusion2 targets where the program uses only ESRAM and/or ENVM. The device setting must be modified to match the actual target device, SmartFusion or SmartFusion2, on the target board. The demo design targets the SmartFusion2 M2S010, so I have to modify the device setting. Refer to the SoftConsole 4.0 release notes for additional information about the OpenOCD command line options and scripts. By default, SoftConsole will debug using the first FlashPro 5 programmer it detects. If there is no FlashPro 5 connected, then it will use the first FlashPro 4 or FlashPro 3 that it detects. There are no issues when there is only one FlashPro programmer connected in the system. In some cases, more than one FlashPro programmer may be connected, in which case SoftConsole needs to be told which one to use for debugging. A specific example of this is a Microsemi Security Evaluation Kit board. On this board, the J5 connector is a FlashPro connector normally to be used for FlashPro programming of the FPGA and SoftConsole debugging. There is also an onboard SPI-only FlashPro 5 programmer which can be accessed via connector J18, which is also used to access the serial ports in the design. If both J5 and J18 are connected to the host computer on which SoftConsole is running, then SoftConsole needs to be told to use the FlashPro programmer connected to J5 for debugging. To use a specific FlashPro programmer when there is more than one programmer connected to the target board, add the following line in the Debug tab Config Options field after the board script line. Where the USB port number XXXXX will vary with the programmer used. Select the Common tab. Here, the Save As local file option is selected by default. This causes the debug launch configuration to be saved in the workspace. If the Shared Filed option is selected, then the debug launch configuration is saved into the project, which aids in portability as it means the debug launch configuration moves in tandem with the project, for example, when copying or exporting or importing the project. Checking the Debug option in the Display in Favorites menu ensures that a debug launch configuration is available the first time the debugger is launched. After creating the debug launch configuration, click Debug to launch the debugger. The Confirm Perspective Switch dialog box will open. Click Yes to open the debug perspective. Check Remember My Decision to prevent the Confirm Perspective Switch dialog box from opening when the debugger is launched. The application will be downloaded to the target board and the debug perspective will open, indicated by the Debug button. The application will be suspended at the first executable line in main. Click the Resume button to run the application. At this point, all the typical debugging activities are available. Click the Pause button to suspend the code execution. Breakpoints can be enabled, disabled, or removed in the Breakpoints view. Breakpoints can be added by clicking to the left of the line numbers in the editor. Cortex M3 register contents can be viewed in the Registers view. Variables can be observed and modified in the Variables view. Variables can also be added to the Memory view by selecting the variable name, right-clicking, and selecting View Memory. The variable will be visible in the Memory Monitor view. The default Memory Monitor view rendering is hex, which may render values in Big Endian rather than Little Endian form. If this is the case, then switch to traditional or hex integer rendering, which renders the values as Little Endian. Additional memory monitors can be created to view other memory locations. Click the plus sign to create a memory monitor. Addresses or expressions can be added in the Memory Monitor dialog box. Click the I symbol to open the disassembly view. The disassembly view will be visible next to the editor and shows the C code and the assembly code. Click the Resume button to resume execution of the code. Let's take a look at the application running on the target board, which is the SmartFusion2 starter kit. The SmartFusion2 CSoC FPGA is shown here. The board is powered by a USB connection, which also provides serial communication with the host PC. The test setup includes a Flash Pro 4 programmer, which is connected to one of the USB ports on the host PC, and the 10-pin JTAG header on the starter kit. OpenOCD uses the Flash Pro JTAG programmer for debug access to the target CPU. One LED on the target board is driven by the PWM core in the FPGA fabric and gradually gets brighter and dimmer. To terminate the debugger, click PWM_slow_blink_elf in the debug view, then right-click and select Terminate and Remove. Click Yes when prompted about terminating. For additional information on the Libero SoC version 11.7 and SoftConsole 4.0 flow, please refer to the SoftConsole 4.0 release notes. Microsemi has also published a tutorial with design files that describe the flow. The SoftConsole 4.0 release notes, the tutorial, and design files can be downloaded using the link shown here. Thank you for watching this video.